Welcome to the Deep Dive. We're the show that takes a whole stack of information, boils it down, and gives you those key insights, basically a shortcut to being genuinely well-informed. Today, we're diving into the really fascinating world of event-driven applications. We're doing that by taking a close look at Emil Kutanov's book, Effective Kafka. It's quite a guide. So our mission today, pretty clear. We're pulling out the most important nuggets of knowledge from this book. We want to give you more than just the facts. We're after those surprising details, the practical stuff that really makes a difference when you're building things. We'll start with why distributed systems are tricky in the first place, then walk through Kafka's core design, how people use it, and tackle some advanced bits like security and transactions. This isn't just theory, We're aiming for that real-world understanding. Okay, let's start unpacking this. You might think, hey, distributed systems, they simplify things, right? Break it down. But one of the first big points the book makes is, well, no, they don't actually reduce complexity. They just shift it. It moves from the individual parts to the whole system, often making the total complexity higher. We're talking about things like debugging, profiling, performance, and especially state consistency. They all become like an order of magnitude harder. And microservices, they're great, but they bring their own headaches too. Tracking all those instances, versions, dependencies, it's described as a Herculean challenge.
It's interesting, isn't it? Because even if you set up asynchronous communication, message queues and all that, you can still end up with what's called transitive dependency. Like service A talks to B and B needs C. Even if A never directly interacts with C, it's still kind of dependent on it directly. You end up with the coupling you tried to avoid. And resilience.
Yeah.
A single big system might just fail completely, simple enough to grasp. But distributed systems, they can fail partially, intermittently. You even get these weird Byzantine failures where parts send bad info. The more components you have, the higher the chance something somewhere will go wrong. It's just probability and consistency. Yeah, that's maybe the trickiest bit to nail down. You've got this massive shifting state across many machines. If you want really strong consistency everywhere, the synchronization gets super expensive, super difficult, and that hits your performance hard.
Right. So if those are the challenges baked into distributed systems, how does event-driven architecture, EDA, help? Does it offer a way to build more, sustainable systems?
Exactly. EDA is basically a design philosophy centered around events. An event is just, significant state change, customer places an order, sensor reading changes, that kind of thing. The whole paradigm is about producing, detecting, consuming, and reacting to these events. You have emitters, producers, then consumers, subscribers, and the channels, which are the brokers connecting them. A really core idea here is that emitters are completely unaware of who's listening downstream. They just broadcast, blind broadcasts, essentially. This autonomy is key. It lets different parts of the system evolve independently much faster, and the scaling advantage is huge. Monolithic apps or systems tied to one big shared database. They often choke when you add more components or try to integrate different platforms like, say, multiple e-commerce sites feeding a data warehouse. EDA, on the other hand, tends to scale much more smoothly, often linearly. For consistency, use ideas like the single writer principle for a given stream of events and maintaining causal order. This helps manage consistency outside the specific domain, relaxing the need for global consistency everywhere and enabling, safe parallelism.
Okay, so EDA sounds like a really powerful approach then. It reduces coupling, boosts resilience, and helps you avoid the nightmare of trying to keep everything perfectly consistent all the time. A solid answer to those distributed system headaches. Which brings us right here. If EDA is the architectural pattern, Apache Kafka is, it seems like the dominant player for actually implementing it.
That's absolutely right. Kafka is pretty much the benchmark for event streaming today. You see other products like Azure Event Hubs or Apache Pulsar often mimicking Kafka's APIs. It's become the de facto standard. It's funny, message brokers have been around since, the 80s? Like Tuxedo. But these event streaming platforms are much newer. There aren't really official standards, so Kafka kind of stepped into that role. And technically, it's Java-based, runs almost anywhere, bare metal, cloud, Kubernetes, you name it. Plus, it has client libraries for just about every language out there. Super versatile for developers.
And the industry adoption is massive, right? From small startups all the way up to the tech giants. Any standout examples?
Oh, definitely. Twitter uses it heavily. They process, I think, 5 billion sessions a day for mobile app performance and analytics. Also Kafka and Netflix. Their Keystone pipeline uses Kafka as its backbone. They handle something like 700 billion events a day, over 4,000 brokers running in the cloud. It's staggering. The reason it's so popular is partly the ecosystem. There's a huge number of open source projects that plug right into Kafka Storm, Flink, Hadoop, Logstash, Elasticsearch, the list goes on, and about 100 ready-made connectors too. Makes integration much easier.
So translating that for everyone listening, what kinds of problems does Kafka actually solve day to day, beyond just being a message pipe?
Good question. It excels in a few key areas. First, publish subscribe or pub sub. Producers fire off messages to topics without knowing or caring who consumes them. Classic messaging. Second, log aggregation. Kafka is brilliant as this intermediate durable buffer for huge volumes of logs. It can soak up bursty log data that would overwhelm a normal database, letting you process it later. Think centralizing logs from hundreds of servers. Third, complex event processing, or CEP. This is about finding meaningful patterns in real-time streams of events. It's used in things like algorithmic trading, security threat detection, real-time fraud alerts, really powerful stuff. And finally, CQRS, command query responsibility segregation. Kafka can act as the event backbone to decouple systems across different domains, using that stream of events as the canonical record.
That's a really diverse set of use cases, shows its flexibility. Okay, let's pull back the curtain a bit. How is Kafka actually built? What are the core pieces?
All right, the fundamentals. You have brokers, which are just individual Kafka server nodes. Pretty simple. But then you have Zookeeper. This is critical. Think of Zookeeper as Kafka's external brain or coordinator. It elects one broker to be the controller for the cluster, and it stores all the vital cluster metadata, like which broker leads which partition, configurations, all that. It needs to be highly available itself. You typically run an odd number of Zookeeper nodes, like 3 or 5, for quorum to ensure consistency. And it's actually its own separate open source project, not strictly part of Kafka itself.
Okay, brokers and zookeepers. What about the data itself?
The data units are called records. A record is basically a key value pair. The value is your payload, the actual information. Records can also have optional headers for metadata, kind of like HTTP headers. The key is really important. It's used to group related records together. The Kafka producer takes the key, hashes it using murmur hash 2, usually, and uses that hash modulo the number of partitions to decide which partition the record goes to. A core principle is immutability. Once a record is published, you cannot change it. Not the key, not the value, nothing. This simple fact is actually a reason why Kafka is increasingly used even where traditional message brokers might have been used before. It's predictable.
Right, you mentioned partitions. Tell us more about those.
Okay, partitions. Within a specific partition, each record gets a unique identifier called an offset. This offset acts like a primary key for that record within that partition, allowing for super fast O1 lookups. Offsets always increase monotonically, but they might not be perfectly sequential. Gaps can appear due to features like log compaction or transactions. We'll maybe touch on those later. Each partition also has a beginning offset, or low watermark, and a high watermark, the offset of the next message to be written. Old records can be automatically removed based on time or total partition size. There's a good analogy in the book. Think of a topic as a highway. A partition is like a single lane on that highway, and a record is like a car in that lane. Cars in the same lane stay in order.
That helps visualize the ordering guarantee?
Exactly. Causal order, making sure related events are processed in the order they happened, can really only be guaranteed if a single producer sends all those related records with the same key to the same partition.
And topics, though the highways in that analogy.
Yep. Topics are those named aggregations that producers publish to. You often hear stream used interchangeably with topic. As we said, the producer uses the key's hash to pick a partition deterministically. But here's a major gotcha the book highlights, something people trip over all the time.
Oh, what's that?
While that partitioning scheme is deterministic, it's not consistent if you change the number of partitions for a topic after you've already published data. If you increase the partition count, Kafka will not rehash and redistribute the existing records. So suddenly, records with the same key that used to land in partition 1 might now land in partition 5. This breaks Kafka's key-based ordering guarantee for those existing keys.
Ouch. So plan your partitions carefully from the get-go.
Definitely. Resizing topics with existing data is tricky and often requires careful planning or application-level workarounds. Avoid it if you can.
Okay, so that's producers, topics, partitions. How do consumers fit in?
Consumers are interesting. Kafka supports a very flexible multi-point to multi-point model. Lots of producers can write to a topic, and lots of consumer groups can read from it. And here's a crucial difference from traditional message queues. Consumers have absolutely zero impact on the topic itself. The topic is just an immutable append-only log. Adding more consumers is cheap in terms of broker load. Now, within a specific consumer group, Kafka guarantees that a partition can only be assigned to at most one consumer instance at any given time. So that's the load balancing mechanism. Exactly. It distributes the partitions across the available consumers in the group. It also acts as a kind of fence, ensuring only one consumer processes messages from a specific partition at a time. Consumers keep track of their progress by committing their offset for each partition they read. They basically tell Kafka, okay, I've processed up to this offset. This commit information is stored in a special internal Kafka topic called consumer offsets. By default, Kafka clients might auto-commit offsets every, say, 5 seconds. But for reliable processing, especially at least once semantics, you usually disable auto-commit, enable.auto.comment false, and manage the commits manually in your code after you've successfully processed the records from a pull. That's the standard pull process commit loop.
Right, makes sense. Okay, we've got the core concepts down. How do we actually get this thing running, say, on a local machine for testing?
Getting started locally is pretty straightforward. First, you need Java JDK 8 or higher for Kafka itself. If you want to use a visual tool like Kafka, you might need JDK 11 or higher. You just download the official Kafka tarball from the Apache website and unpack it. Now, the startup order is critical. You must start Zookeeper first. It's a runtime dependency for the brokers. Use the zookeeper-server-start.sh script. Once Zookeeper's up and running, you start a Kafka broker using Kafka server-start.sh. Check the logs to make sure the broker connects to Zookeeper successfully. And Kafka, which you mentioned, is a really popular web UI for exploring Kafka. It's often just a simple Java JR file you can run. It usually pops up on localhost 0.900000 and gives you a nice view of your topics, messages, consumer groups, etc. Super handy for development.
Okay, Kafka and Zookeeper are running. How do we actually push some data in and pull it out, maybe without writing any application code yet, using the command line?
Yep, the CLI tools are great for that. To create a topic, you use Kafka topics.sh create. You specify the topic name, replication factor, number of partitions. While Kafka can be configured to auto-create topics when a producer first writes to one, auto.create.topics.enable, it's generally considered better practice to create topics explicitly. Gives you more control.
Right. And producing?
For producing simple messages, you use Kafka console-producer.sh. You point it at your broker and the topic, and then you can just type key value pairs like mykey.myFirstMessage directly into the terminal.
And consuming?
Kafka console-consumer.sh. Again, point it at the broker and topic. If you add the from beginning flag, it will read all the messages currently in the topic from the start. Without that flag, a new consumer group typically starts reading only new messages that arrive after it connects. After reading from the beginning, the console consumer will just sit there and tail the topic, printing any new messages as they arrive.
And we can see all this happening in Kafka.
Exactly. Kafka will show you the topic you created, the messages you produced. If you run the console consumer with a group ID, you'll see that consumer group appear in Kafka too. It even shows you consumer lag, how many messages behind the latest offset that consumer group is. Very useful for monitoring. There are other handy CLI tools too. You can list topics, delete records based on offsets, Kafka delete-records.sh, and manage consumer groups, Kafka consumer-groups.sh. That last one lets you list groups, describe their state, see partition assignments, and even reset their offsets to specific points, though resetting offsets is usually an offline operation, meaning the consumers in the group should be stopped first.
Okay, CLI is good for quick tests. But for real applications, developers need to interact programmatically. How does that look, say, using the Java client?
Yeah, for Java devs, you just add the Kafka client's library dependency to your Maven or Gradle project. Creating a Kafka producer is straightforward. You provide configuration properties like the Bootstrap servers. An important point the book makes is that enable.idempotence is now enabled by default in recent versions.
Ah, idempotence. That helps prevent duplicate messages on retries, right?
Exactly. It's a huge win for reliability. It basically ensures writes semantics from the producer's perspective, provided the producer gets an acknowledgement from the broker. It also automatically sets sensible defaults for things like retries and acts to wall for durability. For the Kafka consumer, you also configure it with properties like Bootstrap servers, a group ID, and importantly, how to handle offsets. You'll set auto connector set config, earliest or latest, for when a group has no committed offset. And as we discussed, you'll often set enable auto committed config to false to take manual control over committing offsets after your application logic has successfully processed the messages.
That sounds like quite a bit of Kafka-specific setup and logic mingling with your application code. Does the book suggest ways to manage that complexity?
Yes, absolutely. Chapter 6 and 7 dive into design considerations. A key recommendation is creating an abstraction layer, or a facade pattern. You wrap the raw Kafka producer and Kafka consumer calls within your own simpler interfaces, maybe like event sender and event receiver. This insulates your core business logic from all the Kafka connection details, configuration specifics, and error handling nuances. It makes your application code much cleaner and easier to test.
That makes a lot of sense. What other design advice is offered?
Another big one is producer-driven topic modeling. The idea is that the producer, the system generating the events, should structure the topics based on its own domain model. It shouldn't really need to know or care how downstream consumers want to use the data. This preserves that crucial loose coupling of ED. The producer sends events, consumers figure out how to use them. Now, sometimes you do have multiple very different consumers needing the same core data, but maybe in different shapes or formats. For that, the book suggests a staged event-driven architecture, SETA.
CETA, how does that work?
It involves putting intermediate processing stages, maybe small Kafka Streams applications or dedicated microservices, between the original producer and the final consumers. These stages condition the data, transforming or filtering it to meet the specific needs of individual consumer groups. The analogy used is avoiding children fighting over a stuffed toy. Instead of everyone trying to manipulate the original data stream in conflicting ways, SETA gives each consumer group its own tailored view.
Clever analogy. Any other key design points?
Using custom serialization, deserialization is highlighted as the idiomatic approach. Instead of just sending raw bytes or JSON strings, you create custom serializers and deserializers for your application's native data types, like your order or customer objects. This gives you much better type safety throughout your system. For performance, the concept of consumer pipelining is introduced. Since the Kafka consumer.poll method does fetching, deserializing, and potentially some internal processing all in one thread, you can sometimes get performance gains by decomposing this. You could have separate threads, one dedicated to polling, one for deserialization, and one or more for the actual business logic processing. This creates a pipeline. The book emphasizes that the complexities of this pipelining can be neatly hidden behind that event receiver abstraction layer we talked about. And finally, that abstraction layer also makes record filtering much cleaner. You can implement logic in your event receiver to filter out irrelevant records before they even get deserialized, or hit your main business logic, saving processing overhead.
These design patterns sound really valuable for building maintainable and scalable Kafka applications.
Okay, so once you're past the basics, you've got your abstractions, how do you tune Kafka itself? There seem to be hundreds of configuration settings.
You're not wrong, there are a lot. And the book stresses that really understanding these settings and their implications is essential for running Kafka effectively. Interestingly, it argues that most perceived problems with Kafka aren't bugs or broker misconfigurations, but rather misuse of the technology, like not understanding partitioning guarantees or consumer group behavior.
So what are some common pitfalls in configuration?
One surprisingly common issue is simple typos in configuration property names, either in broker configs or client code. Kafka might just log a warning and use a default value instead of throwing an error. This can silently lead to unexpected behavior, maybe even data loss, or ordering issues if a critical setting isn't applied correctly.
Ouch. How do you prevent that? Two main suggestions. First, use the configuration constants provided by the Kafka client libraries, like producer.config instead of typing the string ax. Second, implement type-safe configuration, basically, mapping external config files like YAML or properties files to strongly typed Java classes at startup. This catches typos and type mismatches early.
Good advice. What about just getting clients connected, especially in tricky network environments like Docker or the cloud?
The bootstrapping process is quite robust. Clients don't actually need a list of all the brokers in the cluster. They just need a bootstrap list that's partially accurate. As long as the client can connect to one live broker from that list, it will receive metadata about the entire cluster topology, all the brokers, topic partition leaders, etc. The listeners and advertise.listeners broker properties are crucial here. Listeners defines what network interfaces and ports the broker listens on. Advertise.listeners defines the addresses that brokers tell clients and other brokers to connect to. These might be different, especially in containerized or cloud environments with NAT or proxies.
So that's how you handle Docker networking.
Exactly. With Docker Compose, for instance, a broker might listen internally on port 9092, but you'd advertise its listener as Kafka.9092 using the service name, or an external address port mapping so clients outside the Docker network can connect.
Makes sense. What about configuring the brokers themselves?
There's a configuration precedence. Settings can be defined per topic, then per broker, then cluster-wide defaults in Zookeeper, then the static defaults in the server.properties file. Per topic configs override broker configs, which override cluster defaults. A really powerful feature is dynamic broker configuration. Many settings can be changed live without restarting brokers using the Kafka configs.sh tool or the admin client API. These changes are persisted centrally in Zookeeper. And a simple but good practice. Always explicitly set the broker.ad in your configuration. It makes identifying brokers in logs and metrics much easier. This ID also gets written to a meta.properties file in the broker's log directory.
Okay, brokers covered. What about important client configurations? You mentioned idempotence for producers. Anything else key?
On the client side, setting a client.id is often useful. It's just a logical name you give to your client instance. It helps with tracing requests in broker logs and can also be used for applying quotas. For producers, we talked about AX, 0, 1, all. Remember, AX all provides the highest durability, but also the highest latency because it waits for acknowledgments from the leader and the in-sync replicas. It's the price of durability. Max.in.flight.request.face Fiber.connection controls how many unacknowledged requests can be outstanding on a single connection. Increasing this, default is 5, can improve throughput, especially over high latency networks, but also increases the potential memory usage on the producer if batches build up. We covered enable.idempotence, the preferred approach for preventing duplicates from producer retries. Partitioners. The default partitioner hashes the key, if present, to select a partition. If there's no key, it uses a sticky round-robin approach to fill batches efficiently. But again, that big warning. Changing the partition count for a topic after writing data breaks key-based ordering because Kafka doesn't rehash old data. Plan ahead. Producer interceptors. These let you plug in custom code to inspect or even modify records just before they're sent to Kafka. Useful for things like adding tracing headers, validating schemas, or collecting metrics. Just be mindful of performance impact and thread safety. Batching and linger.badge.size and bytes and linger.m's time delay work together. The producer tries to collect records into batches up to badge.size before sending. Linger.m's adds a small artificial delay, default 0, to allow more records to accumulate, improving compression and network efficiency, especially under moderate load. It trades a bit of latency for better throughput. And delivery.timeout.ms is an overall timeout for the entire process of sending a record, including queuing, transmission, and acknowledgments. It defaults to 2 minutes.
That's a lot for producers. What about key settings for consumers?
For consumers, .auto.offset.reset. Crucial. What does the consumer do if it starts up and there's no committed offset for its group for a partition? Earliest means start from the very beginning of the partition. Latest, the default, means start from the end, only processing new messages. None means throw an exception. Group.id. This string identifies the consumer group the consumer belongs to. All consumers with the same group.id work together to consume a topic's partitions. If you don't set it, the consumer operates independently, requires manual partition assignment, and doesn't get offset management benefits. Heartbeats. Consumers send periodic heartbeats to a broker designated as their group coordinator to show they're alive. Heartbeat.interval.ms controls how often. Session.timeout.ms is how long the coordinator waits without a heartbeat before considering the consumer dead and triggering a rebalance to reassign its partitions. These need to be tuned together. Max.poll.records. This controls the maximum number of records returned in a single call to consumer.poll. The default is 500. Lowering it can help prevent your application from being overwhelmed if processing each record takes a long time, and it can make processing loops more predictable.
Wow, okay. Configuration is clearly a deep topic itself. Let's shift gears slightly. Talk about Kafka's performance. What's its secret sauce, and how does it manage data durability and cleanup?
Yeah, the performance secret sauce, as the book calls it, is really Kafka's reliance on its segmented append-only log. It heavily leverages sequential disk I/O for both reads and writes. And sequential I/O, even on traditional spinning disks, is orders of magnitude faster than random I/O. On SSDs, the difference is less dramatic but still significant. By avoiding random writes and optimizing for sequential access patterns, Kafka achieves really high throughput.
Makes sense. So how does it ensure that data isn't lost if a broker fails? That's the replication part, right?
Exactly. Replication is key to durability and availability. Kafka uses a leader-follower model. For each partition, one broker is elected the leader. All writes go through the leader. Other brokers act as followers for that partition, asynchronously replicating the data from the leader in near real time. Replication is asynchronous, meaning followers can lag slightly behind the leader. The replication dot factor is set at the topic level when you create it. For any kind of production durability, you'll want at least 3. So data for a partition exists on the leader and, say, 2 follower brokers. The min.insync.replicas, or min.isr, setting is critical here. It's configured per topic or broker-wide. It specifies the minimum number of replicas, including the leader, that must be in sync, caught up for producer write with XSL to be acknowledged as successful.
Yeah, so that's the trade-off. Setting min at ISR high increases durability, but might reduce availability if brokers temporarily fall behind.
Precisely. If you set replication.factor 3 and min.insync.replicas 2, then even if one replica fails or falls behind, the leader plus one other in-sync replica can still acknowledge writes. But if two replicas become unavailable, writes with AX, all will fail until at least one catches up. It's a crucial tuning parameter, balancing durability and availability. And if you need to decommission a broker permanently, you need to use the partition reassignment tools first to migrate all the partitions it leads or follows to other brokers before shutting it down. This can involve copying potentially terabytes of data across the network, so plan ahead.
Got it. What about cleaning up old data? You mentioned partitions have offsets and can be pruned. How does Kafka manage log size over time? It can't just grow forever.
Right. Log management or data retention is handled through log segments and cleanup policies. A partition's log isn't one giant file, it's broken into segments. Each segment file has associated index files, offset index, time index, that allow Kafka to quickly find a record given an offset or timestamp those O1 lookups we mentioned. Only the active segment, the most recent one, is writable by producers. Older segments are read-only. Kafka offers two main cleanup policies set per topic via the cleanup.policy property. The default is delete. This is simple time-based or size-based retention. When a log segment's oldest message reaches a certain age, log.retention.ms, or the total partition size exceeds a limit, log.retention.bytes, older entire segments are deleted. It's good for predictable rotation, like traditional log files.
And the other policy, you mentioned compaction earlier.
Yes, the other policy is compact. This is much more sophisticated. It provides fine-grained per-record retention based on the record's key. The goal of compaction is to keep only the most recent value for each unique key. It essentially turns an event stream into a snapshot or a table-like view where older updates for a given key are purged. Think of keeping only the latest user profile update or the current stock price.
How does it actually work? Does it rewrite the log?
Pretty much. A background process called the cleaner scans the inactive clean segments of a log. It builds an in-memory map of each unique key encountered to its latest offset. Then it recopies the segments, keeping only the record corresponding to that latest offset for each key. Records with keys that have newer versions later in the log are simply dropped. Special records called tombstones records with a key but a null value are used to signal the deletion of a key entirely. The cleaner respects these tombstones but keeps them around for a configurable period, delete.retention.ems, to ensure downstream consumers see the deletion marker before the tombstone itself is eventually cleaned up.
Can you give a quick example?
Sure, imagine a user profiles topic using compaction. You publish .alice.email.a@dad.com, then later bob.email.x@y.com, then alice.email.lz@eed.com. After compaction runs, the log might only contain bob.email.x@y.com and the latest record for alice.email.c@aed.d.com. The older Alice record is gone. The active segment is often confusing records, and the currently active segment are temporarily immune from compaction until the segment is rolled over and becomes inactive.
Can you use both delete and compact on the same topic? That sounds weird.
It does seem counterintuitive, right? Like a database silently dropping old records. But yes, you can set cleanup.policy delete compact. This means Kafka will both compact the log to remove old key versions and delete entire segments based on age or size. The primary use case for this is Kafka's internal consumer offsets topic. It uses compaction, so consumer offset lookups are fast, only need the latest offset per group partition. But it also uses deletion as a way to garbage collect offsets for consumer groups that have been inactive for a long time, controlled by offsets.retention.minutes.
Okay, that makes sense for internal topics. This discussion of consumers, offsets, and groups leads nicely into reliability. How does Kafka manage consumer group membership and partition assignments fairly and reliably?
Yeah, group membership is absolutely central. As we said, it's the mechanism for load balancing partitions across consumers and ensuring exclusivity. Only one consumer per group gets a given partition. The group management protocol has basically two phases. First, joining. Consumers send join group requests to the group coordinator. The coordinator waits for a bit, collecting requests from members, acting as a synchronization point. Second, syncing. The coordinator chooses one consumer instance to be the group leader. This leader receives the list of all members and decides which partitions go to which member. It sends this assignment plan back to the coordinator in the sync group request. The coordinator then distributes the assignments to all members in the sync group response. Then everyone starts fetching.
That sounds like it could cause pauses, especially if consumers join or leave frequently. Is that the rebalancing process?
Exactly. When a consumer joins, leaves cleanly, or is presumed dead, missed heartbeats, the coordinator triggers a rebalance. This involves revoking partitions from existing members, running the join sync protocol again, and redistributing partitions. These rebalances can be disruptive, a stop-the-world pause where no one processes messages. Sometimes you get a swarm effect, lots of consumers starting at once, causing multiple unnecessary rebalances. Kafka has introduced improvements over time. There's a group.initial.rebalance.delay.ns setting to add a small delay when a group first forms, reducing churn. More significantly, starting in Kafka 2.4.0, there's incremental cooperative rebalancing.
Cooperative rebalancing, how's it different?
Instead of revoking all partitions from all members during a rebalance, the cooperative protocol allows members to keep partitions they aren't losing. The rebalance happens incrementally over potentially multiple rounds of the protocol. It significantly reduces the stop-the-world pause duration, as consumers can keep processing partitions that aren't affected by the specific join-leave event. It's a big improvement for application availability. There's also static group membership. By setting a unique group.instance.ad for each consumer instance, a consumer can leave, for example for a restart, and rejoin within the session.timeout.ems period without triggering a rebalance and potentially getting its exact same partitions back. Very useful for stateful applications or avoiding slow state restoration.
This whole area of rebalancing heartbeats and timeouts feels like it ties directly into those core distributed systems concepts, liveness and safety. Can you remind us what those mean in this context?
Sure. Liveness essentially means the system eventually makes progress. Something good will eventually happen. For Kafka consumers, it means if a consumer fails, its partitions will eventually be reassigned to another healthy consumer, so processing continues. Safety means the system's critical guarantees are never violated, something bad will never happen. For Kafka consumers, safety includes preserving record order within a partition and, critically, ensuring a partition is assigned to at most one consumer within a group at any time.
How does Kafka ensure those?
Liveness is handled by the heartbeat mechanism. Heartbeat.interval.ems, sessions.timeout.ms. If a consumer misses heartbeats, the coordinator eventually detects it and triggers a rebalance. But proving progress that a consumer isn't just heartbeating but stuck in an infinite loop is harder. Solutions usually involve application-level timeouts, bounding max.pull.records, or more complex patterns. Safety, especially partition exclusivity, is trickier when failures happen. What if a consumer processes a batch, commits the offset, but then fails before its output side effect completes? Or what if it fails after processing, but before committing, and then another consumer reprocesses the same messages after rebalance?
Right, the classic at least once versus exactly once processing problem.
Exactly. To achieve something closer to exactly once processing, beyond just the producer's idempotence, you often need external mechanisms. One approach is external fencing, using a distributed lock manager, DLM, like Zookeeper or etc. Before processing a batch related to a specific key or partition, the consumer acquires a lock. If it fails and another consumer takes over, the new consumer must acquire the same lock, preventing concurrent processing. This adds idempotence but also latency and complexity. Another is process-level fencing. Using an external monitoring system, like Kubernetes liveness probes, you ensure that if a consumer instance has its partitions revoked during a rebalance, the entire process is forcibly killed or isolated before Kafka completes the rebalance and assigns those partitions elsewhere. This prevents the zombie consumer from continuing to process stale data.
Wow, ensuring safety really requires careful thought. Okay, given these group dynamics, how does Kafka actually decide which consumer gets which partitions? Are there different strategies?
Yes. The assignment logic is pluggable via the partition.assignment.strategy consumer config. There are a few built-in options. Range assigner, the default surprisingly. It sorts topics alphabetically, then partitions numerically, divides partitions by consumers, and gives each consumer a contiguous range. It works okay for simple cases, but can lead to uneven load if consumers subscribe to multiple topics, often overloading the first few consumers. Round-robin assigner. This one treats all partitions from all subscribed topics as one big list and deals them out one by one to consumers, like dealing cards. It generally provides a much more balanced assignment across consumers, regardless of topic subscriptions. The book questions why range was ever the default. Sticky assigner. This newer strategy aims for two things. 1, achieve a balanced assignment like round-robin, and 2, minimize partition movement during rebalances. It tries to keep partitions assigned to the same consumer if possible, reducing state churn. Cooperative sticky assigner. This is a sticky assigner adapted to use the newer incremental cooperative rebalancing protocol we discussed, further minimizing those stop-the-world pauses. This is often the recommended strategy in modern Kafka versions.
It really feels like we're peeling back layers of complexity here. Kafka is powerful, flexible, but definitely not simple. Using it correctly seems to demand a solid understanding of these distributed computing principles: liveness, safety, consistency.
That's a perfect summary. It's a complex beast designed for demanding use cases. You can't just throw data at it and expect magic without understanding how it works and configuring it properly. A good grasp of concurrency and distributed systems theory is almost a prerequisite for using Kafka effectively at scale.
Let's switch gears to another critical area: security. You mentioned earlier Kafka isn't secure out of the box. That sounds alarming.
It is something to be very aware of. Let's be crystal clear. Kafka has numerous security features covering authentication, authorization, encryption, but they are all disabled by default. Out of the box, any client on the network can connect to any Kafka broker and often to Zookeeper nodes too, including diagnostic ports. Zookeeper especially is a potential treasure trove for attackers as it holds cluster metadata. Also, by default, all communication client to broker, broker to broker, even broker to Zookeeper is unencrypted plain text, easily sniffed, potentially altered, or impersonated.
Okay, that's not ideal. Before we fix it, what should a secure Kafka setup look like? What's the goal?
The goal is always minimizing the attack surface area. Limit network access to only the absolutely essential endpoints for legitimate clients and brokers. This relies heavily on robust, logical network segregation.
So what's the first line of defense? How do we start locking it down?
Network traffic policy, implemented via firewalls. This is fundamental. You need to segregate your network segments. The book recommends a clear separation. Zookeeper nodes should be in their own highly isolated network segment, accessible only by the Kafka brokers. The Kafka brokers themselves reside in another dedicated segment, protected by a stateful firewall from the client network. Clients live in their own segment. And then there's the broader external network. Firewalls are simple, efficient, and hard to bypass when configured correctly. They should be your first step. For remote access, like developers working from home or edge applications, use VPNs and potentially client-side certificates to securely tunnel traffic into the appropriate client network segment. Kafka itself shouldn't need to be directly exposed.
Network secured. What about protecting the data in transit? Snooping, tampering.
That's confidentiality and integrity, achieved using TLS-SSL. Kafka supports TLS for encrypting client-to-broker traffic and interbroker traffic. Setting it up involves creating a certificate authority, or using an existing one, generating key pairs and certificates for each broker, signing them, and configuring brokers and clients with trust stores and key stores. You should also enable hostname validation, ssl.endpoint.identification.algorithm.https, to prevent man-in-the-middle attacks. A key limitation noted in the book, as of Kafka 2.4.0, was the lack of native TLS support for the connection between brokers and zookeepers, though work KP513 was underway to address this. You need external solutions like network tunnels for that specific link if required.
Okay, traffic is encrypted. Now, how do we verify who is connecting?
Authentication, right. Exactly. Authentication proves identity. Kafka supports several mechanisms: mutual TLS, MTLS, also called client-side certificate authentication. Not only does the client verify the broker's certificate, standard TLS, but the broker also verifies the client certificate, signed by a trusted CA. The ssl.client.auth broker setting can be none requested, allows but doesn't require client certs, useful for migration or required. SASL, Simple Authentication and Security Layer. This is a framework for pluggable authentication mechanisms. Common options include SSL plain, simple username password. It offers no encryption itself, so it must be used over a TLS connection. Usernames passwords are often stored in Zookeeper or a JSConfig file, says the Scram. A more secure challenge response username password mechanism, ScramChe256 or ScramChe512. It provides protection against eavesdropping even without TLS, though using TLS is still recommended. It also provides mutual authentication. The broker proves its identity to the client too, generally preferred over plain. Sesloth Bearer uses Oath 2.0 bearer tokens for authentication, often used for integrating Kafka with existing identity providers or for simplified testing using unsecured JWTs in non-production environments. Requires implementing custom callback handlers for token validation in production. Delegation tokens, a Kafka native mechanism useful for large clusters or temporary credentials, like in Hadoop environments. Users authenticate once, for example via Kerberos or MTLS, to obtain a short-lived HMAC-based delegation token. Applications then use this token ID and its HMAC secret as SESL username password to authenticate without needing long-term credentials. These tokens can be renewed.
What about authenticating to Zookeeper itself?
Kafka can authenticate to Zookeeper using SASL, but Zookeeper's own built-in support, as of version 3.5.x bundled with Kafka 2.4, primarily enforces authorization via ACLs, not mandatory authentication for connections.
Yeah.
Restricting Zookeeper access relies heavily on those firewall rules we discussed earlier.
Okay, we've authenticated the user or application. How do we control what they're allowed to do? Read from topic A, write to topic B, create topics, etc.
That's authorization, and Kafka primarily uses ACLs, access control lists, for fine-grained control. It's a rule-based system with a default deny model. If no ACL explicitly allows an action, it's denied.
Yeah.
ACLs grant permissions like read, write, create, describe, delete, alter on specific resource types, topic, group, cluster, transactional ed, delegation token, to specific principals, usually users identified via TLS or SASL, like user.alice. If a client tries an operation that's denied by ACLs, the Kafka client library will throw a specific authorization exception, like topic authorization exception or group authorization exception. You manage ACLs using the Kafka-lscls.esh command line tool or the admin client API.
Is there anything tricky about how ACL rules interact?
Yes, a very important point. Deny rules always take precedence over allow rules. This means you can't grant broad access with an allow rule and then try to revoke specific parts with deny rules for the same principal resource. It won't work as expected. The deny will always win. The recommended pattern is to start with the implicit default deny, add specific all rules for what's needed, and then, if necessary, add more specific deny rules to card out exceptions within what you've already allowed. This creates up to 3 tiers: default deny, custom allow, custom deny. The book also advises against using host-based ACLs, allowing denying based on client IP address, for application access control in dynamic environments like cloud or containers. Firewalls are much better suited for network-level restrictions. Use principal-based ACLs for application authorization.
It really is a layered approach then. Network, encryption, authentication, authorization.
Exactly. It has to be. Because threats aren't just external hackers. Accidental misconfigurations, internal issues, buggy applications, they can all cause problems. A layered defense provides resilience. Security needs to be built in, not bolted on afterwards.
All right, one final piece related to security and resource management. Quotas. How do they fit in?
Quotas are a natural extension of security, particularly addressing the availability part of the CIA, confidentiality, integrity, availability triad. But they're also crucial for ensuring quality of service, QoS, and fair resource usage in multi-tenant clusters, or just preventing runaway applications from impacting others. The main goal is mitigating denial of service, whether malicious or accidental, like a buggy consumer spinning wildly. And in shared environments, they allow for rational allocation of broker resources, network bandwidth, and CTU without resorting to excessive over-provisioning.
What kinds of quotas does Kafka offer?
There are 2 main types. 1, network bandwidth quotas. These limit the rate, in bytes per second, at which clients can produce or fetch data. Separate quotas for produce and fetch. This directly impacts network usage, but also indirectly affects broker I/O, memory, and CPU, especially with SSL. 2, request rate quotas. These limit the percentage of time a broker's network I/O thread spends processing requests from a client. This primarily targets broker CPU utilization, preventing clients from overwhelming brokers with too many small, frequent requests. It's measured as a percentage, making it somewhat resistant to vertical scaling of the broker. Adding more CPU cores doesn't automatically increase the quota.
How are these quotas applied?
Quotas are enforced on a per-broker basis. This is a key point. A client interacts with multiple brokers, leaders for different partitions, so its total cluster-wide throughput is roughly the per-broker quota multiplied by the number of brokers it's actively communicating with. A notable drawback mentioned is that a client's effective quota can therefore dilate or increase as you add more brokers to the cluster, which might not be the intended behavior. Enforcement uses a basic sliding window algorithm. The broker tracks client utilization over small time windows. If a client exceeds its quota, the broker simply starts delaying its responses to that client, forcing it to slow down implicitly.
Who do the quotas apply to? Users. Client IDs.
They can apply to authenticated user principals and/or client IDs. There's a precedence order. A quota defined for a specific user and client ID takes highest precedence, then a quota for just the user, then a quota for just the client ID. Finally, there are default quotas per user or client ID. Importantly, all clients sharing the same user principal and/or client ID that matches a specific quota rule will share the capacity allocated by that quota.
So, that delay-based enforcement, how well does it handle bursty traffic? And does the client even know it's being throttled?
You can tune the quota window size and number of samples to influence tolerance for bursts versus enforcing a flatter traffic profile. More samples or longer windows allow more burstiness. But a significant challenge is the lack of explicit feedback. The broker doesn't tell the client, hey, you're exceeding your quota. The client just sees increased latency and potentially timeouts. This can be confusing and might even lead to counterproductive behavior like more aggressive retries, potentially worsening the situation similar to a congestive network collapse. The book notes Kafka lacks a mechanism to clearly signal quota enforcement back to the client.
Okay, that's quotas. Now let's tackle maybe the most complex talked about topic. Transactions and Kafka's approach to exactly once delivery. Sounds like the holy grail.
It is definitely a complex topic, and the book gives it significant attention. Let's start with the preamble. Transactions arrived in Kafka 0.11.0.0 via KIP98. It was a massive undertaking. Years of planning, dozens of related KIPs, thousands of tests. Impressively, the performance overhead was kept relatively low, maybe a 3–5% throughput reduction on average. And it's crucial to understand that the idempotent producer feature we discussed earlier is actually the foundation for transactions. They share much of the same underlying mechanism, producer IDs, sequence numbers. The core problem transactions solve in Kafka is ensuring exactly what semantics specifically within consume, transform, produce workflows. Without transactions, if your application consumes message A, produces message B based on it, but then crashes before committing the offset for A, you could reprocess A after restarting and produce a duplicate B. Transactions prevent this.
How do they work then? What changes for producers and consumers?
For transactional producers, the key new concept is the transactional.id. This is a stable identifier you configure for your producer application. It allows Kafka to ensure continuity across different instances or restarts of your producer application. Each transactional.id is mapped to a specific broker acting as its transaction coordinator. The producer uses a simple API in the transactions, begin transaction, then sends its records, potentially multiple send calls, optionally sends consumer offsets to include in the transaction, send offsets to transaction, and finally calls either commit transaction or abort transaction. All messages sent between begin transaction and commit abort are part of that atomic unit. For stream processing applications like consume, transform, produce, you typically use pinned producers. This means you maintain a separate Kafka producer instance for each input partition your application instance is assigned. The lifecycle of these producers, creating, initializing, closing, needs to be carefully managed within a consumer rebalance listener as partitions are assigned or revoked. This ensures causal linkage between input records and output records produced within the scope of that producer's transaction.
Okay, sounds involved for the producer side. What about consumers? Do they need to change?
While most of the complexity is producer side, transactional consumers do have a role, mainly related to isolation. The key is setting the consumer configuration isolation.level read committed. The default is read uncommitted, which means consumers see messages as soon as they're written by the producer, even if part of an open transaction. With read committed, consumers will only see messages that belong to transactions that have been successfully committed. They will never see messages from aborted transactions. Internally, this works using the last stable offset, LSO. Transactional consumers don't just read up to the high watermark, the latest physically written offset. They read up to the LSO, which is the offset of the first open transaction in the log. This effectively prevents the consumer from reading past any ongoing transaction until it completes, commits, or aborts. Aborted records are filtered out and never delivered to the application.
That sounds powerful, but are there limitations? It doesn't sound like a universal distributed transaction solution.
Absolutely not. There are important limitations. 1. Kafka bound. It's a proprietary Kafka protocol. It only works for operations involving Kafka topics, producing messages, committing consumer offsets. It cannot coordinate transactions with external systems like databases or other message queues. No XA or JTA support. 2. Cannot span producers. A single transaction cannot span multiple Kafka producer instances if they have different transactional.ads. All operations within one transaction must be performed by producers configured with the same transactional.ad.
So, pulling it all together, are Kafka transactions overhyped, or are they genuinely useful? What's the verdict?
The book offers a nuanced take. If your application's processing logic and side effects are already naturally idempotent, meaning processing the same input multiple times produces the same end result, then you might not even need Kafka transactions to achieve effective exactly once end-to-end semantics. A well-written consume process produce loop with idempotent operations can suffice. Where transactional messaging really shines is in eliminating duplicate records within complex event stream processing graphs, especially when applications rely heavily on Kafka itself as the primary event store. And dealing with potential duplicates at the application level would be difficult or error-prone. Frameworks like Kafka Streams can encapsulate much of the complexity of managing those pinned producers and transaction lifecycles, making it much easier for developers to leverage exactly once semantics without handling all the low-level details. It's important to remember the general impossibility dictum of true exactly once delivery across arbitrary distributed systems. Kafka transactions provide exactly once within the Kafka ecosystem for consume, transform, produce patterns. They don't magically solve it for interactions with external databases or APIs. For those scenarios, you still need to implement idempotency or other coordination mechanisms yourself. Ultimately, the book suggests that for many common event-driven applications, perhaps the most practically useful aspect that came out of the transaction work, P98, is actually the idempotent producer. Just enabling that provides significant guarantees against duplicate records caused by network retries, ensuring cleaner data lands in Kafka in the first place, even without using the full transactional API.
Wow. Okay, that has been a truly deep dive. We went from the fundamental pain points of distributed systems through Kafka's architecture brokers, zookeepers, topics partitions, consumers, then into practical operations, configuration nuances, and finally these advanced critical topics like security, quotas, and transactions. We've really tried to give you that shortcut, boiling down the essentials from effective Kafka, mixing the what with the why it matters, and highlighting those specific details that can make or break a Kafka implementation.
Absolutely. If there's one thing to really take away from all this, it is that Kafka is no trivial creation. It's powerful, yes, but complex. It's built to handle a huge range of streaming needs, but using it correctly, especially at scale, isn't straightforward at all. You really do need that solid grounding in distributed systems concepts, liveness, safety, consistency, to truly harness its power effectively and avoid the pitfalls.
So here's a final thought for you to consider, building on everything we've discussed. Given Kafka's inherent complexity, its power, but also its nuanced features like transactions, security settings, and quotas, how can an organization best cultivate the deep, specific expertise needed within its teams? How do you move beyond just using the defaults or having only a partial understanding to truly mastering Kafka and leveraging its full potential reliably? Something to think about. That's all for this deep dive. Thanks for tuning in.